Hey, welcome back. It's another Scrumptious Jimmy video, and I've managed to come up with a pretty nice integral that's actually not too hard to solve. Well, it doesn't take too long to solve, it's still not elementary, but it's also very instructive, and it shows some nice relationships between some real functions and their complex analogs. So yeah, we have this integral, which is generalized in terms of the parameter alpha, and it resembles one of the integrals I previously did on my channel. You can see that video for yourself, but I've added a sine x in the denominator, and of course we have this parameter just right next to the sine x in the logarithm. Yeah, and after playing around with it, I found that the domain restrictions on alpha are actually not too bad. Alpha can be any complex number, but if it's real, it can't be less than -1. Let me quickly illustrate that. So the great idea here on the domain restriction is we don't want the logarithm to have an argument of 0. So that means we can't have alpha sine x equal to -1. So I'm just gonna do that. We can't have alpha sine x equal to -1 within our bounds, because if this is -1, cancels that, we get 0, and boom, -infinity, we're discontinuous. So this means that sine x cannot equal -1 by alpha from 0 to pi over 2. So for any positive alpha, you can easily see that, it'll say sine x cannot be a negative number, which sine can be negative, but from 0 to pi over 2, it's only positive, so we're actually fine. But if you take a number, let's say, less than -1, let's take -2. The negatives will cancel, and we'll say sine x cannot equal 1/2, but we all know sine x equals 1/2 at pi over 6, which does, in fact, fall within our 0 to pi over 2 range, which is bad. So that means we'd have a discontinuity there, and yeah, we can't have that. But if you noticed, at -1, we actually would have a discontinuity, but at pi over 2. Because it would be that sine x would have to equal 1 in order for it to be discontinuous. But we all know that if the discontinuities at the bottom are top bound, we can play around with it a little, and sometimes it still converges, which in fact it does converge here, and I'll solve for that value later. But I do want to mention, while we have it here, that alpha can be complex, because if we take some complex number, let's just say just do 1 plus I, any random complex number. Sine is never going to have an imaginary part from 0 to pi over 2, since we're dealing with the reals. So yeah, so that's why alpha can be complex. Anyway, so yeah, I guess there's not much else to do, but let's just get into solving it. But stick around at the end after I solve it, because there's some pretty nice operations I'm going to do. You'll see. So I'm going to start off the same way I did with the similar integral on my channel. I'm going to stick in a new variable in place of the alpha. It's going to be y. And I'm going to evaluate this from y equals alpha to y equals 0. Because at alpha, we'd recover our I of alpha, sorry. And at 0, this term would go to 0. We have an ln1, which is 0, which means it'll go to 0, which means we don't need to, we don't need to balance anything out. We don't need to add any extra terms. So now we can change this to a double integral. This is my favorite integration trick, honestly, other than complex stuff. You'll see. Anyway, so integral from 0 to pi over 2, that's x, and from 0 to alpha, that's y. But now we have to differentiate the integrand partially with respect to y, which we know will give us a 1 plus y sine x in the denominator. But by the chain rule, since we're differentiating with respect to y, we get a sine x in the numerator, which cancels this one. So in the end, we get this. dy dx. Now by Fubini's theorem, since it's still going to converge if we switch the bounds, or the order of integration, I'm going to switch the order of integration. So now we've got dx dy, and our bounds have been replaced. And now the classic technique for this kind of structure is to use the Weierstrass substitution, which removes all the trig functions and turns them into polynomials, which are much easier to work with. So recall that that substitution would be x equals 2 arctangent t, implying dx equals 2 over t squared plus 1. Okay, now we have to figure out what sine x is going to turn into in the t world. So I'm going to use the same proof as I did for the other integral I did. So we can rewrite this as t equals tangent x by 2. So that means our angle is x by 2, and its tangent is t, so t over 1, opposite over adjacent, which means we know this is square root of t squared plus 1. And now we want to find out what sine x is, but keep in mind its argument is double the angle we have in our imaginary triangle. But we all know that using the double angle formula, you can get sine x equals 2 sine x over 2 times the cosine of x over 2, which these are known values. So it's going to be 2 times, sine is going to be t over this. The cosine term is going to be 1 over the hypotenuse. Well, adjacent, you get it. So this will end up equaling 2t over t squared plus 1. So, great. We can sub that in for our sine x. So we're going to have a 2 from the differential element. That's a z-looking 2, even though I dash my z's. Anyway, so 0 to alpha. Now let's take care of our bounds, actually. So at 0, we'd have, we can get rid of the 2. So 0 equals arctangent t. We know that the lower bound has to be 0. That's a terrible integral. 0. So then, remember, tangent x over 2 is t. So x is pi over 2. So then we need tangent pi over 4, which is 1. And then we're going to have 1 over 1 plus y, and then we have a 2t here, so I'm just going to do 2yt over t squared plus 1, and then times our differential element, the rest of it, that is. Forgot a dt here. So then we have dt dy, and then we can slide in this t squared plus 1 to the numerator of the denominator, which will cancel this out and just replicate itself on this 1. Not x. T squared plus 2yt plus 1. Just move stuff around a little bit. dt dy. And now I'm going to use the trivial substitution of t going to x, because everything's better when it's in terms of x and y. No one likes dt dy. So, yeah. So nothing changes, just the variable does, which we all know doesn't matter for a definite integral. So, okay, here we are. We've got this structure, but trust me when I say we don't want to start integrating, we don't want to try to find the antiderivative of this yet, even though we can. Let's just first do something. Let's take this integrand, let's just go over here. But first, I'm going to make x equal 1 over x. That's going to be our substitution. So dx equals negative 1 over x squared of our new dx. So we're going to have 2 integral from 0 to alpha, then integral. So we're going to have 1 over 0 coming from the right, which will be infinity. And then 1 over 1 is 1. And then I'll use the negative from the differential to immediately switch the bounds. Then we have 1 over x squared plus 2y over x plus 1. And then we have the rest of our differential dx dy. Again, we can slide this x squared in. And then after I move around a couple of terms, we get x squared plus 2yx plus 1 dx dy. Which is the same exact integrand we had before. So that means since we've got two identical copies of our integral, we can add them together and halve them in order to still recover our integral. So once we add these, the bounds, we're going to have an integral from 0 to 1 plus an integral from 1 to infinity, which means we'll get an integral from 0 to infinity. And we have to use this 1/2, which will conveniently cancel out this 2. Okay, now we can get to working on this. So first we're going to have to complete the square. So we know to complete this square, we're going to have the coefficient of the cross term. I said have, by the way, like divide by 2. So, and then we have to square it, and that's what we have to add. So that means we're going to have 1 over, after adding a y squared, because if we have 2y, we get y squared, y squared. We're going to have x plus y, x plus y quantity squared plus 1, but then we need to have a minus y squared just because of, since we added the y squared to begin with, we have to balance it out. Then we have, oh, I forgot one of the integrals. Okay. Apologies. Okay, dx, dy. Great, so now we have an arctangent situation here. So we can take the antiderivative, which will still just give us, we'll have our y bounds. Now remember, it's going to be 1 over the square root of the constant, and the constant is 1 minus y squared. So we're going to have a 1 over square root of 1 minus y squared. And then we're going to have the arctangent of x plus y over square root of the constant, which is square root 1 minus y squared. And then we evaluate from infinity to 0. Then we have dy. So at infinity, this term will go to infinity, which will give us a pi by 2. So, yeah, okay. So at pi by 2, we're going to have, sorry, at x equals infinity, the inside goes to infinity, arctangent infinity is pi over 2. At 0, the x just disappears, and we'll have this arctangent term like this. So we can rewrite it, and keep in mind we're subtracting the x equals 0 term. So this is going to be times pi over 2, and then minus the arctangent of y over the square root of 1 minus y squared. Yeah? Another parentheses. Yep, okay. Now let's evaluate this integral. So that means we're going to have, after distributing, so first of all, let's just notice, I don't even have to write this yet. We distribute this, we have pi over 2 times this, but we know that's arcsine, right? And that's just the arcsine structure. So that means from these bounds, we're going to have arcsine alpha minus arcsine 0. Arcsine 0 is 0. So that means we just have pi over 2 times arcsine alpha. And then we have minus this integral. Dy. Okay, now, when I first saw this, I was like, whoa, this can't be solvable, right? But actually, this, like, collapses very, very easily. There's a couple ways I can do this, but I'll do it the fun way. So, let's look at our arctangent. Oops, small triangle. We want big triangle. So, let's look at our arctangent. So, we want to figure out what this is equal to. So we have some angle, let's just call it like theta. So that means the tangent of this angle is this. So that's opposite over adjacent. So in order to find the hypotenuse, we just got to square this. So y squared plus the square of this, which is 1 minus y squared. We know hypotenuse is 1. So we can find another way to write this arc trig function because it would still be a representation for whatever angle it's talking about. So we can actually simplify this so that we don't have this nasty argument of the arc-trig function. Let's choose something simple, like the simplest thing here would be y over 1. So let's just take the arc sine of y over 1, which is just y. So here, I'll put a parentheses here. So notice arc sine y gives you the same thing as arc tangent y over square root 1 minus y squared. So that simplifies it. But now what? Actually, it's very, very simple. Because remember that this is the derivative of arc sine, and we've got that exact function in the numerator. So a simple use substitution is in order. And along these bounds, we'll just get this. Because this is what we substituted for. Dang it. And boom. That is the formula for our answer. But we are most certainly not done yet. I've got some more things on my agenda. So, now, this is, in fact, a solution for our integral. But let's notice something. Let's notice that the domain of arc sine is from -1 to 1. But, Daniil, didn't you say that alpha could be any complex number as long as it's not real and less than -1? Yes, it can be greater than 1 as a real number. So, explain this. Well, what if I told you that even if you... So, first, for those of you who don't know, the reason there's a domain restriction on arc sine is because if you stick in a number that's greater than 1 or less than -1, you will get an imaginary number. An imaginary angle will be what arc sine spits out. Excuse me. So that means we'd start getting imaginary numbers. But what if I told you that all the imaginary parts would cancel out, no matter what? If you plug in 2, 5, a million into arc sine, even though, of course, in the real plane, you can't have sine of an angle having a magnitude greater than 1. But all the imaginary parts would cancel out, and that's what I want to show. Now, notice that, yes, it'll also work for like -2, -5, minus a million, but with our original problem, we can't take those into account because of the integrand. So, what I seek to do is rewrite this function because its domain isn't very large. And we want to find expressions for our total domain of alpha. And yeah, so let's see what we can do about that. Okay, so let's recall a definition of sine of x. So, using complex numbers, we know that this is equal to e to the ix minus e to the minus ix over 2. The proof is very simple. It's just you take Euler's formula, stick in an x and then a minus x, and you subtract the two equations, and then you divide by 2i, sorry. So this is sine x. They are completely equal. Feel free to prove it if you wish. Just, you can expand these, and then the cosines will cancel out, and yeah. Okay, great. So, now, we have arc sine alpha. So, that means we want our sine to equal alpha, right? Because if we're taking the arc sine of alpha, we're saying that the sine of what angle is alpha. So, sine x equals alpha. Now, let's move some stuff around. This is actually a pretty common trick. Some of you have probably seen it before. So we have it like this. And now I'm actually going to write this formula up here just so that we don't forget it and so I can erase it since it's at the bottom of the board. Great. Okay. So now the trick is we're going to multiply e to the ix on both sides. So we're going to have e to the 2ix minus 1 equals 2I alpha e to the ix. Now, moving it around, we have e to the ix, which e to the 2ix is just this squared. Then we have minus 2I alpha e to the ix minus 1. And we have this all equal to 0. So now we can use our quadratic formula, since that's exactly what we have here. But keep in mind, we don't just have an x here, we have an e to the ix. So that means we have to solve e to the ix equals, now let's just use our quadratic formula. We have negative b, which would be 2I alpha, because our b is negative 2I alpha. Then we have plus minus the square root of b squared, which negative 2I alpha squared would just be minus 4 alpha. And then minus 4ac, which would be negative 1 times 1 times 4, which is minus 4, but since we subtract it, we add 4. Oh, wait, alpha has to be squared. And then we divide by 2a, and a is 1. Now, we can factor out a 4 in this square root, which means that after we take out the square root 4, we get a 2. So that means, and then we can use this 2 to divide out the 2's in the numerator. We'll have I alpha plus minus the square root of 1 minus alpha squared, since the coefficients are gone. Okay, now, this works with the principal value of arcsine and sine here. So just trust me when I say the positive version of this is what we're looking for. Because, you know, let's think about in the real plane, for example. Sine can be 1/2 at pi over 6, but it can also be 1/2 at 5 pi over 6. So we have sort of the same thing going on, but we're just going to take the principal value. So yeah, this is what we want to deal with. But now keep in mind this is e to the ix. So that means we're going to have to do some manipulation. So to get x, we have to take the natural logarithm and divide by I. Well, take the logarithm of both sides and divide by I. So that means this is equal to ln of I alpha, oh, sorry. I have to write log I alpha plus square root 1 minus alpha squared. That's at alpha. But now remember that 1 over I is actually just equal to minus I. So I think it's simpler to write this. So, okay, great. We've basically just taken the inverse of this function. So now, believe it or not, remember we had sine x equals alpha. We've just solved for x. And we know that x equals arcsine alpha. And now we have the principal value of this function. So, believe it or not, these two functions are actually the same when you consider complex numbers, which is kind of baffling. I mean, just look at this. We've managed to expand this seemingly harmless function into a mess of imaginary numbers and a logarithm too. Yeah, all right. So all that means is that we can substitute in this monster for arcsine alpha in our formula. So let's do pi over 2 times minus I I'm just not going to say it because you can see it. Yep. And then we have a minus, and then we got to square this. So when we square I, we're going to have a negative 1, and this negative is going to go away. So that means we're actually going to get a plus since we were subtracting it in the first place. Let's make sure we're still recording. Okay, nice. Right? Yeah, okay. So now we've managed to rewrite this formula we had before like this. So I want to do something here though. Remember that the entire reason I performed all these operations was because I didn't like how our arc signs have a domain of -1 to 1, and even though, yes, the imaginary parts are going to vanish if you put in a greater number, we don't want our final answer to be like, if we plugged in 2, we don't want pi by 2 arc sine 2. Like, that's an imaginary, it's got an imaginary part, and it doesn't really give us a familiarity with the actual answer. But this strategy will. So now let's expand a little something in this logarithm. So I want to notice that since we're looking outside of the range of -1 to 1, notice that this term will be imaginary, because this square root here will only be real if alpha is from -1 to 1. So all I'm going to do is basically factor out a negative, like this. So we're going to have now alpha squared minus 1 times -1, or times -1, okay? So that should be fine, but we know the square root of -1 is going to be I here, which, yes, it could be -I, but we're taking principal values. So now let's just do that to both logarithms. Let's just put a minus I pi, put the minus I there, then we have log. So now we're going to have that I, but that means we can factor out an I because we have an I here as well. So we're going to have I times alpha plus square root of alpha squared minus 1. And then, of course, plus this. Okay, nice. But now we know we can split the logarithm because we have a multiplication in the argument. So we're going to have log I plus log of this. And we know log I is going to be e to the I, or sorry, we know I is e to the I pi over 2. Its logarithm is I pi over 2. So that means we can write this as I pi over 2 plus, now we can just do ln because we don't have any more imaginary units. Okay, like that. And then we do the same thing here. And we have to square this. So let's get to reducing. So the minus sign to I here will turn positive, so we're going to have a pi squared over 4, okay, right, because we have a -1 and a negative here already. Yeah, and then we have a minus I pi over 2 ln alpha blah, 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 blah. Yep, let me just verify I'm not being stupid here. Okay. And then we're going to have to square this. So that means let's take this term squared. We know that's going to be minus pi over 4. Well, actually, I'm just going to throw in the divide by 2 for each term. So we're going to have a minus pi squared over 4, which will become a minus pi squared over 8. And then we have to take 2 times the cross product, which will be I pi ln this. But then we have it, so that's going to be plus I pi over 2 ln this. And then we take this squared. Over 2. Okay, great. Now, we notice these two are the exact same, so they cancel. And whoa, look at that, no more imaginary parts. Now let's just put it all together. Pi squared over 4 minus pi squared over 8 is pi squared over 8. Then we have, let me write this a little neater. So now, all of a sudden, we have another expression for our integral, which is actually very bizarre when you think about it. Let me actually write this up here. Okay, so shockingly, this is perfectly equivalent to our original formula, which just like, how? I mean, all we did is like rearrange stuff with complex numbers, and all of a sudden we have an equivalent but obviously very different formula. But notice that if we plug in, real numbers into this, we'll get real numbers out. If we plugged in any real number to this, we get a real number out because the imaginary parts would cancel. All this does is show that the imaginary parts would cancel. But now, let's look at why having both of these is very important for the domain. So notice that arcsine is, remember its domain is from -1 to 1. So on like the graph, which I graphed I of alpha on the thumbnail, but logically these graphs should be the same. But arcsine is just from -1 to 1. It's kind of like that. And then this, if you plug, so go into Desmos, put this in, you'll have from -1 to 1 of this. And then if you plug in this term, you'll have the exact same thing, just from a different domain. This thing's domain, notice that we know this domain is from -1 to 1, but notice that if alpha is from -1 to 1 in here, this square root becomes imaginary. Well, you get square root of negative numbers, so it's imaginary. So that means we sort of have this union of the domains, because now this domain is from 1 to infinity. So we've basically, by having both of these functions, we've combined the domains, and now we have a more comprehensive expression for this. So now, remember, we didn't want like arcsine 2 in our answer. Now, if we plug in stuff here, we're actually going to get a real answer. Not just in terms of these functions, which you might not know what they equal. But now, let's keep in mind, alpha could be complex, which, as I said, these are both perfectly sufficient for complex numbers, because if we look in the complex plane, the only reason this had a domain restriction is because it's going to be complex, or it's going to have an imaginary part if the alpha's magnitude is greater than 1. And for this has a domain restriction of 1 to infinity, because if alpha had a magnitude less than 1, you'd still get stuff with imaginary parts. But in the complex plane, that's fine. So that means in the world of complex numbers, these two functions are exactly identical. Like, right down. Then you can see visually, if you graph it in Desmos, that they're just part of the same curve, but they represent different ranges of x values, which I just think is like crazy. This is really cool. I mean, yeah. So what I wanted to do is just plug in some numbers and, give like a little table of values for this integral. Yeah, I do want to mention though, this result does look a little suspicious, because this is just 3/4 times zeta 2, and this is actually inverse hyperbolic cosine of alpha, and then divided by 2 makes it look like we U substituted for inverse cosh, which makes me think there might be another way to solve this integral, but I took like every single angle I possibly could, even after I got this and then derived this, and I found no way to actually get this result in any other form, well, using any other process except the complex sine trick. So let me know in the comments if you can actually solve this integral and just get this formula immediately, which, to be honest, I'm hoping there isn't a way, because it would just make this a lot more cool. But if there is, it means I didn't look hard enough. But anyway, let's just plug in some values, and what is it? Oh, actually, everyone should enjoy when I write the final answer. So let me just write. I just want everything to be nice and neat. So this is the final result for our integral. Now I can erase all this stuff. Gotta make sure we're still recording. Okay, so now I just want to make a table of values here. So let's do I of 1. So we can use the arc sign for 1 since it's within its real domain anyway. So we'd have pi by 2 times pi by 2, because sine of pi by 2 is 1, plus pi by 2 quantity squared over 2. Yeah. Ah, no. I almost messed up. Ha ha ha. That's a minus sign. So it's this, which means we have pi squared over 4 minus pi squared over 8, which is pi squared over 8. So I of 1, so when alpha is equal to 1, our integral becomes pi squared over 8, which should be obvious if you plug in 1 here as well, because this would make the square root 0, and you have ln 1, which is 0. So this term vanishes, and you get pi squared by 8. Now, I kept bringing up, like, plugging in 2, so let's find the actual value. We're not going to have pi by 2 arcsine 2 minus arcsine 2 squared over 2. Now, we're going to have pi squared over 8 plus ln squared of 2 plus, then square root of 4 minus 1 is 3, so 3 over 2. That is our answer. Go ahead, plug it into Wolfram alpha. This is correct. So, yeah. Okay, we've got another thing. Now, I'm feeling a little bit cheeky, so let's do I of I. So, it's not going to make much sense if we plug in arcsine I, so we're just going to use this formula again. So that's going to be pi squared over 8 plus, now I squared is negative 1, so that's going to be square root of negative 2, which we know is I root 2. Now we can split this up again. We're going to have I pi over 2, because we can factor out the I, and then its logarithm is I pi by 2. What was it? So it was 1 plus root 2, right? Because we had an I here, and then a I root 2 there. So yeah, this should be right. Square this. So then once we get that, we're going to get I pi over 2 squared, which is minus I pi by 4, but then we have a minus, but divided by 2 we get minus, wait. No, I pi over 2 squared is negative pi squared over 4. Okay, I think I said an I. So that's going to be minus pi squared over 8, which will cancel this out. Then we need the cross term, which will be, what is it? This. And then our final piece. Just making sure I'm doing this all right. So we doubled it, but then it was halved. So we have this. These two vanish. And hold on. Is that it? Yeah. Okay, so that's what I of I is. Yeah, I think I've exhausted pretty much everything. Wait. Before I conclude, let's do I of minus 1, just because we do have a discontinuity with alpha being minus 1, but it's fine, because it still works for this formula. So we'd have a minus pi by 2 from here, and then we have a minus times minus pi by 2 squared over 2, which this would be pi squared over 8. So when you subtract that, from this, you're going to have minus pi squared over 4 minus pi squared over 8. So that's minus pi squared over 4 minus 2 pi squared over, wait, no. Minus 2 pi squared over 8 minus pi squared over 8, which is minus 3 pi squared over 8. Okay, I think I've messed around enough with values of alpha. But yeah, I mean, I think this was really awesome. I hope you guys do too. I mean, the transition between these two and the fact that they're equal is just mind-boggling. And just like how they work with the domain is just awesome. So yeah, I hope you guys enjoyed. This problem was very unique. I haven't found one that actually was this interesting. But hopefully I'll find more. And please subscribe, comment, like, blah, blah, blah. Do all that stuff. Bye.